before going back to Arc Apex, I'd like to go through a few things about the database. So first, if you remember, I was creating these, folders to do Arc Apex projects, and these are not complete. These are all incomplete. So there are things that are missing in this current folder, but just to let you know, if you go to this folder, then these are the files, ArcMap, MXD file, and then folders, subfolders. And if you need to use those, shape files like sub-area boundaries, rich definition, stream definition, and outlets and others, then you can go to the watershed folder. And then shapes subfolder has things like, river definition, sub-area definition, and then other shape files like a mask that we just created and other things. In the grid folder, it has those raster layers that we linked to Arc Apex, all stored here, all this here. And then if you go to the scenarios folder, then currently we have only default as being the subfolder here. There will be more subfolders if we create different scenarios other than the default, simulation within Arc Apex. We'll do that later on this afternoon. So if you select this default subfolder, there are several subfolders, and currently there's no scenario or anything. But if you go to the txt in out, again, this is empty. But this folder, txt in out folder, is the location where you will have all the Apex input files written by Arc Apex. So when we go through all the way to running the Apex model, then if it's a default scenario, then it will be the txt in out subfolder that will have all the Apex input files and output files. So from there on, you can actually take those files into another folder and then just directly work with it for calibration and other purposes, and post-processing and others. Let's go to the C drive where we installed Arc Apex. So C Apex and then Arc Apex was the folder we had, Arc Apex installed. So here, you can find Apex 1501 underscore debug 64.exe and then release 64.exe. These are the actual Apex executables. So these are the Apex models you can call. Okay. So here, you can see that the debug version is much bigger in size than the release version because debug version executable contains all the debug information, line by line information. So if it crashes while running, then it will print out those information like, okay, which subroutine, which line in what subroutine it crashed because of this issue, things like that. Debug information will be printed upon failure. Release version does not contain any debug information, so it will, if it crashes, then it will crash without giving meaningful, error information. It will just crash. But on the flip side, debug version will run much slower than a release version, of course, because while running during the runtime, the debug executable should maintain all the debug information alongside the actual model simulation. So that's why it's bigger than the release version, and that's why we're providing these two executables at the same time. So if you modified Apex input files outside our interface programs like Arc, Apex, Apex Editor, or whatever, and then made a mistake unknowingly, and then so the Apex model crashes, then you can run debug version and then read the error message, and then be able to fix the error. Release version crashes, then that's it. It just crashes. But if you have all correct input files, then you can use the release version because it runs way more faster than the debug version, and especially when you calibrate Apex in like 100 or 1,000 iterations. It's a time-consuming process, and you want to use the release version executable than the debug version executable. So those are the stuff that you need to be aware of. And then let's go to the databases folder, where we have a lot of things in the example Apex subfolder, but this time we'll open the apex.mdb file. You have Microsoft Access program installed on your computer. If not, then you can just follow me here. So if you open the apex.mdb file, you will see a bunch of tables. All right, all these tables, many tables. So here you have we have an LCD LU catalog table. So an LCD has a specific rule for defining different land use types, and land use numbers are very specific, and then they keep the same kind of naming convention between different versions. So we actually tabulated that land use numbers here in this table. So if you chose USGS and LCD while loading land use map, right? Then you actually load an LCD land use map into ArcApex. Then ArcApex will actually look up this table instead of you having to provide a table, and then find out how these numeric values correspond to a land use name that Apex recognizes. And again, as you may have noticed, these are all like a 4-letter names that we prefer to define a crop or land use type. And why this is an important step. If you go to the crop table, which is here, table crop com, you will find that the crop name here, crops are mostly defined in 4 letters or 3 letters, but no more than 4 letters. There's a rule that we just made. There's no really any really meaningful reason why we are stuck with the 4-letter naming convention, but it is what it is. And if you look at the stuff here, we have soybean and corn, grain, sorghum, and so forth, cotton. And then down below, we have like other things like urban, water, commercial agriculture, wetland, forest, and all those are defined as a type of crop or plant. So your land use lookup table should have the land use name which should appear in this table. Okay, so if you have orchard, then you named it, let's say 33, then that 33 has to be linked to ORCD so that the Apex, Arc Apex can link that 33 to orchard, and then any land use type that has 33, and its name on the land use map, spatial map, will be linked to this line, and then recognized as orchard. Okay, so same principle applies to all others. And soil definition is same. Let's see. Oh, soil, user soil. Yeah, here. User soil. We have list of soils, but mostly Vermont. But we also offer US Sorgo. Tabular information for the Sorgo soil database as well. So you can just incorporate any Sorgo soil into your soil map, or you can use the Sorgo soil map. So these are all different tables that are used to build your Apex model during the process of developing Apex input files. And these preferably should not be modified or customized as much as you can. So if you want to add more or update any of these tables in this file, then my recommendation is that you just make a duplicate of it and then use that to add more or customize, and then keep it separate from this default database file. So that way you can always come back to the default settings and the table values. So you have the pristine settings always available for future model development. So crops are there, fertilizers are there. So in this fertilizer table, we have a little over 70 different kinds of fertilizers defined. They are basically defined by the fraction nitrogen, phosphorus, and potassium, and then between organic and inorganic components. And then additionally, organic carbon contents and salt contents. This is a cost, if I remember right, like a kilograms per, dollar per kilogram, something like that, or dollar amounts per kilograms per hectare application, things like that. So that cost information there, and each type. These are, like a some are commercially available, some others are like a more elemental form for modeling purposes, meaning like a 53 will be a pure nitrogen. So if you apply 20 kilograms per hectare of elemental nitrogen, then did I say 23? 23 kilograms, then that entire 23 kilograms will be actually the nitrogen. Then what else? If you have selected other types like a manure having only 0.2% nitrogen, so you have to many tons of nitrogen to actually supply, let's say 100 kilograms per hectare of nitrogen to the field. So that's the kind of computation you need to do to apply proper amount of nutrient using these particular types of fertilizer. So that's it. In the till table, we have different tillage operations. We have many operations, and they are categorized into different types by IHC. So it's more like a tillage ID, type ID, but you know, between 0 and how many? 15, something like that. Oh, we have up to 26, 25, 26. Yep. We categorize them into planting operations, harvesting operations, fertilizer application, irrigation, pesticide, and many others, right? So you can add more operations here and then provide what the, you know, efficiency is. Okay, I'm doing tillage with this, and then let's say like this. Then I'm doing tillage and weeding and so forth, and then okay, what will be the efficiency? Okay, so plowing efficiency is 80%, and then that means okay, not about 80% of the soil will be completely mixed, and then 20% will not be between soil layers within the plow depth, and then or tillage depth, and then you specify what tillage depth you will be tilling the land under this operation. And what else? Other details will be set by giving numbers in these columns. Some are cost related, parameters. Some others are efficiency or type or depth, rich high, rich interval, things like that. And also tractor information comes here. So you can select a, like a, I don't know, I don't know much about tractor, but different types of tractors with the different machine, fuel efficiency or the rich width, things like that, so that you can actually simulate the proper number of tillage operations going back and forth. How many lifts you need to complete the tillage of this field, things like that will all be set here with the proper tillage ID. Pesticide information comes from this pest table. We have number of different pesticide, and many are commercially available, and they are characterized based on what are all these, some are like organic versus inorganic, and I don't really know much about pesticide, but these 1, 2, 3, 4, 5, 5 different columns will characterize individual pesticides for modeling purposes.
This is Susan. So for each table, you will have a table definition, so that will give you what the variables mean.
Yeah. Let's say, for example, crop table. We saw this table before. Has like 50 something, 55, 57 columns to define a crop, and those crop parameters include WA is more or less radiation use efficiency, RUE, which is more commonly known, and then harvest index, optimal temperature, base temperature, maximum leaf area index, the time that the senescence will occur in terms of leaf area index value, plant population versus LAI relation in S-curve, those parameters all here. So like how tall a crop can grow. So here, for example, 0.8 meter, and then a maximum root depth 2 meters down. It's its harvest index is 0.3, meaning about 30% of the total above ground biomass can potentially be soybean grains. That's harvestable. It will not grow below temperature Celsius. Maximum leaf year index can go up to 5. So, depending on the plant population, every year, if everything works fine and then grows well, then leaf year index can be up to 5.0. Things like that all written here to characterize a soybean. So this can be used to create another sibling soybean parameter and different varieties. If you have, like a, what could it be? Like, it can grow better in cold regions with lower base temperature, for example, right? Or it can actually grow a lot taller than 80 centimeters height as the maximum height. Things like that, depending on the genetic characteristics of the soybean that you're particularly simulating, you can update, modify these parameters to best reflect the physiology of the crop here on this table, and then add it to the bottom of it, and then give a number there, unique number. Then you can actually use it in the Apex simulation. All right. Then now we'll go back to our Apex. And I'll quickly redo from scratch up to the point where we stopped. So some of you might want to follow me to recreate a project. Those who failed to go to the next step while for creating sub areas. So I'm going to create a new project, and I'm now saving the document. And then for the project directory, I'll go back to the D drive, and then I'll create, okay, I have up to 3. So then this time I'll create a folder named DX4. And then select it. Make sure that EX4 is selected under the name, and then click OK. OK, same, OK. So OK to create a new project. Then the next step is to go to the automatic sub-area delineation. We'll select Apex standalone delineation menu, where the first thing I'll do is to load a DEM from the disk. And then I'll look for the example, DEM, which can be found in the Apex and ArcApex and databases, and then example Apex folder. So going into these subfolders, 4 layers down, you can find DEM or DEM 10 meter either way. I'll choose DEM, and then you should have this DEM loaded on your ArcGIS ArcMap. Then I'm not going to touch this for now. I'll make sure that I'll address this and then the burn-in, stuff in the near future. So I'll load a mask from our existing example data set. And so now have our, northwest corner kind of masked. And then we'll do flow direction and accumulation calculation, followed by create streams and outlets. Okay, now I have this stream network defined, and I'll just take it. Yep, we could add additional outlets on any of the channel network, we can't create an outlet point outside those channel lines, because outlet means a channel outlet. It has to be on the channel. And creating an outlet means you are actually splitting your sub area at that point. So at that point, there will be an outlet from a sub area, and then that will flow into its downstream sub area, which you just split it now with that additional outlet. So I will not do that now, but I'll just choose the whole watershed boundary, and you left click and then drag it to include a point that you want to take as the watershed outlet, and then release the mouse button to finalize your selection and click OK. Then now you see the delineate watershed button is activated, meaning you can click it. Then Arc Apex will use that point as the outlet of the watershed, and anything that does not drain into that point will be removed from your watershed model. So if you remember, we had a few, pieces of channel lines going outside this current the watershed boundary before we did the delineation. But then now they are all gone because they don't flow into this watershed outlet point. So I'm gonna just calculate sub-area parameters now. Let me know if I am going too fast. But this is all the process we already went through at least once or several times. So I'm assuming that you understand, you can kind of follow me if I go at this speed. All right, so everything calculates sub-area parameters. This is a bit tricky. Maybe I should just create a alert that okay, this is done or something like that. Yeah. But it's done now, so you waited enough, and then everything's right. Number of outlets 14. We had 15 earlier, but now we ended up having 14 sub-areas. So we'll exit and then go to the next step. Are we all good? Luca, everything good? Audio, video?
Yep, everything is fine, Jack.
Okay, yeah. Just want to make sure that I'm not get lost.
Yeah, no. Okay.
All right. So next is land use, soil, and slope definition. If you remember, before launch, we loaded these map layers and then overlaid, right? So we loaded from disk and then projected land use map there. And this land use map can be anything of your choice, or the way that you prepared, as far as you know how to link these numeric or whatever land use name to the land use names that are in the Apex crop table. So we'll select the value field on this land use map, and then provide a lookup table to link these numeric names to actually 3-4 letter Apex land use names, then reclassify. Now we have linked this land use map to the land use types listed in the crop table. Then next to the soil, the same thing. So I'm going to just load stats go. Let's save a few seconds. Then I can skip a lookup table because everything is already formulated in the Apex MDB file. Then classify. Then the next slope, I'll just take single slope because no big deal for training purposes. Okay, so I have just a single slope and then land use map, soil map, all loaded and reclassified, and then now ready to overlay the 3 map layers. Then each pixel will get a combined land use, soil, and slope information. Okay, so now here is where we stopped. Are we all here? Good. I'll take it yes. Sub-area definition is the next thing. So I was explaining what these really mean, right? Three different things. Well, user-defined is basically you just manually assign particular land use, soil, and slope, okay, for each and every sub-area. So it's a full manual assigning of all these properties. You can, there are total 5 different land use types in the watershed. There are 2 different types of soils and then 1 slope class. So you can just, select this or that, or this or that, and then this as the, a nominal property of sub-area 1. And then sub-area 2, you provide different things. If you know everything, right? If you know what land use type you want to assign to sub-area 2, what soil you want to assign to sub-area 2, and then what slope, then you can actually do it all this full manually. Otherwise, you can let ArcApex basically do the spatial analysis thing. So between the first and second, second is dominant land use, soil, and slope combination that's spatially referenced. So all these, we're talking about overlaid property. Once overlaid, each pixel gets land use, soil, and slope kind of combined property, right? And then the predominant combined property of the subarea will become the nominal property or used to define the subarea. That's the second option. First option is if you have not thinking of a special overlaying. You may have a large area with corn, but then they are not really necessarily spatially overlapping with other major soils or slope classes. Then still, if you chose one, then still the corn being the most dominant land use type, corn will be selected as the land use for this particular area. I mean, all these sub areas. But if you selected second, then corn will not be selected. Maybe somewhere pasture will be selected because it has more pixels that share common properties in the sub area. So then some pasture will be the dominant land use type. So you see the difference between this first and second option, right? But for physical modeling, the second option is typically the go by choice, and we set it default. So I'll just I'll leave it as default selection. And then it will calculate all the pixels within each and every subarea and identify the percent, number of pixels with this particular combination of properties, and then rank them from largest to the lowest, and then kind of use the majority as being the sub-area properties. So that's how this ArcApex will define a sub-area. Okay, so we're done up to this point. So if you look at, let's say this one, final sub-area distribution report. Then what you will see is, okay, for the entire watershed, total this many hectare. It's about 483 square kilometers area, and then and on the average watershed average summer pasture actually occupies 96% of the area, total watershed area. So this is predominant, the predominant crop growing in the entire watershed. Corn field actually comprises only 3%. That's it. Summer pasture and corn. We had other, oak, soybean, range, those land use types as well, but they were too minor, okay? And so they are ignored during the sub-area definition. If, let's say, soybean is like 0.1%, then even though they are there, our capex will just, ignore them and then take the majority crop to represent the sub-area. And after all, we ended up having 90-something% of summer pasture and then 30-something% of corn. That's it in the model. So model represent basically the majority, the dominant properties of the watershed, but not the entirety. If we want to keep those minor types, then we can use the user-defined sub-area definition and then elaborate our selection for those particular crops that way. Once we're there, then now we got to incorporate weather station data. It doesn't have to be weather station, ground-based station. It can be reanalysis data, grid-based, or whatever. Basically having those point locations for either ground-based weather station or weather, grid points, kind of cataloged in a text file, and then with the name, and then that name file, another file, a DLY file containing all time series weather data, okay, climate data that include precipitation, temperature, relative humidity, wind speed, and solar radiation. You don't have to have all these daily time step weather data prepared to make APEX simulations. You can just completely rely on weather generator. We offer WXGN weather generator based on NOAA's NCDC historical weather data. Is a daily weather data collected from all NOAA, and it's like what they call it, affiliated or whatever, personally owned but the volunteered weather stations data, still managed by NOAA, are compiled to represent local weather characteristics. So the weather generator WXGN will run this US climatic weather database to create daily rainfall values, daily min max temperatures, and other relative humidity and others. And those will be based on local measurement. So those numbers from the weather generator will still be reasonably acceptable to represent local climate. If you have daily climate data, weather data measured and then available, then you can incorporate that historical weather data into APEX model from here. So in the case of our example data set, we have precipitation and temperature data available for this watershed. And So you check what type of data are available, or you will simulate using observed inputs. If you leave them blank, then that means you will use weather generator to create these values. And then you browse to the location table, which will be found again in the Apex, C drive Apex, Arc Apex, databases, example Apex. So same way, right? It's all same way. Where we have a file called wdlstcom.txt. It's more like a daily weather station, list. And I can actually open it here. It's just a list of weather stations in terms of their ID, name, and then latitude, longitude, day, period, the data are available. So that's it. But mainly it is these first two columns that are most important. Others are optional. And you strictly follow the format and the order in terms of columns. So in your, because we will load this file, this tx 1040.dly will be listed as weather station number 1. And then it will look for this file if any subarea is assigned with weather station number 1. That means you need that file prepared. And here, these are the files that are already prepared. And actually, Dr. Sario will show you how to actually write DLY files from your observed data, like a Excel format. You can easily export a DLY file from your observed values, and then just copy it to the folder for simulation. So we will demo that part as well. So now, boom. So this is a location table, and then it will read those weather stations written in the list, and then copy them into the folder. Now we have the weather station information imported, and then if you have point discharges, then this is the part you enter point source discharge information input. And or like if you select it, this is a new round. In the morning I incorporated point sources, but this round I didn't. I skipped it, so I don't. But if I had incorporated a point source in the watershed, then that choosing this menu will trigger a window to input point source characteristics like discharge amount, sediment concentration, NPK, loading rate, things like that, salt as well. The next step is to write default inputs to our personal geodatabase file, MDB file, out of apex.mdb. And then this watershed definition so far we have. So we're going to select all and then click OK. And then exit. Because it's all written. Next step is either edit the inputs that we just wrote to the MDB file, or we write actual Apex input files, meaning we'll be writing text files that are all actual Apex input files. So we'll write them. Then now exit. We're all down here. Then now we can actually make Apex run. So that's the default run scenario, and we have everything okay. Just run Apex. We'll open this DOS command window and then run Apex in that DOS command and then complete. So that's it. Well, that's it. That's it. what really happened just now is if we go back to our project folder, and then again, scenarios folder, default, and then txt in out folder. Now, we didn't have anything in this folder earlier, but now we have this bunch of files, right, created, right? But we don't have the Apex executable, right? That's why I showed you that in the C drive, Apex, ArcApex, we have these files, right? So these files need to be copied. I mean, for Apex run outside ArcApex, okay? ArcApex knows where to find these executables, and then it can run them when you have these input files in another folder, because it knows path, the path. It can actually relate this folder to the executable and then run it. Otherwise, you need to copy this executable into this folder and then double click to run it. It's the same thing. We just run Apex outside ArcApex, okay? And then what you get some output files there. Okay, but they all name the same. This site 14, right? That's something. Does this seem kind of familiar here? That's a run name. Site 14. You can name it differently, and then whatever name you give to there, that will be the name of your all output files, and then your output file extensions will tell what those output files are about, and we'll get to there later in a few minutes. So now we have completed Apex model development, and we ran Apex inside ArcApex, and then I showed you how to actually make Apex runs outside the interface program. Well, we can actually create different scenarios here. So first, let's actually import these text outputs. Let's say not this RCH is not available now, but let's say this SAO is a sub-area output that is specially developed. So that's annual values for all sub-areas. We had 14 sub-areas, and then these are like PT value was this much, actual ET was this much, irrigated, not irrigated, was snowfall or snowmelt flow occurred, annual precipitation amount. All these are part of the output, information that the model prints out. Now, there we have a couple of output files that we can actually import into Apex output.mdb file. They are RCH and SAO. So you click them and then click import. Then now these outputs in txt format, not output.rch, this one, site14.rch. That's the actually rich output file. So see, this is all formatted text. So, a little tricky to really deal with numbers in terms of visualizing time series values, things like that. You prefer them to be on Excel or some sort of tabular, right? So then you just imported those to apex output.mdb. That's here. Scenario default, we had all the input files, output files in the txt in out, right? Now you go to the tables out subfolder, and that's where you can find the output.mdb. And if you open it, then you have two tables, RCH, and then this is actually a SAO file. So if you just cross-check, the MDB file and the actual RCH output file, then they have to be the same. So let's see the first line. Let's look at water yield output 0.05, 0.05. So yeah, they are the same. They are the same information. So it's basically just importing these numbers in the text format into access format. It's nothing but just loading it that way, importing the text file into Excel, not Excel, access table. Same thing here. So you can actually export these numbers for plotting and other purposes. So that's one functionality we have. And then you can save this whole project into a different scenario. Let's say scenario 1, for example, and then save. Then it says, okay, this run successfully saved in this folder. EX4 scenarios, scene 1. Okay, let's see what it is. EX4 scenarios. We had only default folder, right? With this. Now we have another folder, scene 1, right? Same kind of configuration, and then txt in out having the same thing, right? So it's just duplicated this default folder and then renamed it to scenario 1. That's all what it did. But then now, because this is scenario 1, let's see, we can modify some settings or simulation options to make it a really different scenario from the default scenario. Let's say, oh well, yeah, I'd like to edit Apex inputs, for example, right? And then these are available Apex inputs: control table, site table, sub-area file, herd file, soils, print options, palm or landscape, wind erosion, LWE. Let's look at the print option. We have, I told you that we have a number of different print files. You see, there's, long dragging to see the complete list of output files. And if you click it, then there's some description you can see on the bottom, so you can actually pick and choose which one else other than those already selected you can print. So let's say we want to print one of my favorite is ACY here, which is annual sub-area crop yield. So you can click add to include ACY in the output file. Then in your previous simulation, if you go to the txt out, sort it by date, then you had only out, RCH, SAO, SUS, SWT, all those except for ACY, right? So those are created because they were turned on, all others turned off, right? So now I have included ACY. And then also maybe daily sub-area file. SAB, daily sub-area file, is the output file that prints daily values of sub-area related output variables. So I'm going to include it as well, and then save, exit, then exit. Now, what you need to do is because we edited Apex inputs, we need to rewrite Apex input files. Okay, so we're going to select all and then click OK, and then exit. Then what we do, we rerun the Apex model. Everyone following me? Okay. So now let's see. Boom, 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 boom. Oh, okay. Well, unless I guess what it's doing is when we create a new scenario, then it just kind of archives the current settings into that particular scenario and then continues whatever we are. So when you create scenarios and then simulate, then you archive it with a new scenario name, but then you are still with the default so that you change other settings for another scenario and then run it and then save them in another scenario. So that way you can actually create multiple scenarios. Just saving, and then here, okay, oh, here's actually setting. We can set actually scenario 1 as a default now. Then you know what I'm saying? You create a scenario, make a model run. No, this one. So we created a scenario. So here we created a scenario, right? And then saved it. And then we need to change to that scenario if we want to make it active, current, okay? So to switch from default to default from scenario 1, then we need to do this part. Otherwise, the scenario 1 that we saved will be saved as a inactive, scenario there. So that is sort of one further step to just keep us stay in the new scenarios as we create new ones and then rerun Apex. Because we created scenario 1, but then didn't actually select this as the new default, our changes in the output setting actually happened in the default scenario. So the ACY file was created here instead of scenario 1. Okay, so if we chose scenario 1 as the default, and then let's see if we have those. No, so okay, so if we edit and then include ACY, save, and then write, and then run. So you see the pattern, the process that I'm repeating and repeating, right? Then scenario 1, txt in out. I don't know. I thought it should create ACY here. Apparently, I think I'm kind of going back to where it was. All right, that's a little tricky there. I need to clarify myself first before addressing that anymore. Another thing that I would want to do the exercise is edit Apex database. So this edit Apex database allows to edit those important tables in the database file. So for example, you have a crop that you want to add to the crop table, then you can do that directly from the apex.mdb file, but then also you can do it here by adding a new crop and then providing the crop parameters. And you can do that by copying one crop to another. So these are the all available crops currently for simulation in Apex. And then also you can modify these crop parameters by editing, clicking the edit crop button, and then actually modifying individual boxes. And these crop parameters you can find these descriptions by double clicking in the text box for editing. Then you can find what they mean, right? This RLAD, leaf rate index decline rate parameter, 1, less than 1, larger than 1, what they mean, these values mean, all here you can find those meanings. So you can edit those crop parameters. And then also operation schedules can be updated, edited, or modified here. So we have these default management operations, but now let's see here. For example, corn, grain crop, medium tillage is a name, and then it is a 1-year rotation, as you can see. So just 1 year, starting from April 1st until September 11th to kill it, right? And before kill it, we harvest it like day before killing it. And then we also fertilize it. Let's see how much fertilizer we're putting. So we're putting 65 kilograms per hectare of fertilizer. In terms of fertilizer application, is kilograms per hectare, right? So 65 kilograms per hectare of fertilizer, number 53. And what that means is an elemental nitrogen. Like I said earlier, if you go back to the fertilizer table, then all fertilizers are defined in terms of their fertilizer ID. So you can select fertilizer ID to select a particular fertilizer. Then that means 65 kilograms of nitrogen to add to the field. So you fertilize the field first, and then plow a couple times, and then here April 15th you plant, and then see, cancel, then let's go to plant, and then here you're planting soybeans, which is crop number 1. If you go back to the crop table, then the soybean is the first thing you will see on the top. So soybean is planted here, and this is potential heat units, meaning how many heat units it needs to really go from planting to harvesting. So this is needed to simulate the proper growth curve, and also in case you use heat unit scheduling, which we will talk a lot more tomorrow, you need this value to determine when to harvest. Other things like genetic settings in terms of if automatic irrigation is set, then this is the ID in the tillage table that this will pick to do automatic irrigation. And then fertilizer, again, automatic chemical fertilizer, manure, or other types of fertilizer, if implemented, then these are the numbers that Apex will pick for this particular operation schedule, and then implement. So this is a 1-year rotation, as you see, but this can extend into a 2-year rotation with let's say winter cover crop. As you can, after killing soybean, you can plant let's say winter wheat October 2nd, and then keep it grow until the following year, year 2, let's say March 2nd to kill it, and then plow it to incorporate into soil. And then next, year 2, you plant corn, for example, right? And then kill. So you make a 2-year rotation. Then what it will do is it will repeat the 2-year rotation over and over every 2 years. So we'll have soybean, winter wheat, corn, and then soybean, winter wheat, corn. It will continue that way. If you simulate 20 years, then it will repeat 20 years. If you simulate 100 years, then it will repeat 100 years with the 2-year rotation operation schedule. And you can either create a brand new schedule within Arc Apex, or you can also use Apex editor to create your own operation schedule for your own crop. Because Arc Apex has very limited option in terms of providing operation schedules. So it's not really handy in terms of putting together a specific cropping system schedule for cropping system. Ooh. 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 It's an error. Yeah, these errors are just crazy. I mean, they just pop up from nowhere, and I don't know. Okay, crashed again. Maybe, as I just go back and forth a few steps, jumping around, kind of messed up the links and the databases and so forth, and then just forced ArcGIS to crash, I guess. And that's okay. I mean, I've seen so many times this ArcGIS crashing, especially running Arc Swallow Apex. So if that happens, and if you had all the model developed, then that's fine. If not, then I always recommend that you start from scratch. And if you repeat these model development processes a few times, then well, first time it will take a couple days. Second time it will take half day, and the next time and beyond it will take like 1 hour, and then 30 minutes, and then 5 minutes, and then 3 minutes. So ultimately it becomes kind of no-brainer to get to the entire model development in a very fast time. So don't get frustrated if you see those this ArcGIS crashing on while doing something, some process in Arc Apex. It's a I would say limitation of Arc Apex or ArcGIS. We don't know which side the error is coming from, or maybe some error at the interfacing of the two. So that was the thing. One thing, if Javier is here, I want him to kind of go over briefly how to build DLY files and WP1 monthly weather statistic files using the Apex editor tool. And then we'll come back to Arc Apex to do one last exercise, which is, okay, we have this, default outputs from the default simulation. And then we want to add, let's say, irrigation to a subarea where the subarea was set to do rain-fed system, but then we want to change it to an irrigated field, and then see how that influenced the model output. So we're gonna kind of do an exercise for that as the last thing for the day. I have a few other we have a few other exercises available for practicing like this. So if needed, then we can do some other exercises as well. But that is actually the plan I have. All right. Why don't we take a 5-minute break? It's over 1 hour time. So let's take a 5-minute break, and then when we come back, we'll learn how to edit inputs to add certain practices to our operation schedule. And then especially automatic irrigation as the first thing, and then maybe the fertilizer as well later on. And then weather input stuff, we will cover that tomorrow morning when Javier comes back. I guess one thing that people are a bit confused is how this operation schedule works with simulation period, or during the simulation period, do we need to write the operation schedule all the way through 5 years, 100 years? No. Like I said, 1 year rotation can be written for that particular 1 year as year 1, and then month day, and then during the simulation it will just repeat that 1 year operation over and over. So for example, if we go to the edit Apex databases and then operation schedules, and then find the summer pasture, if we can find summer pastures right here, right? You see there's only 2 lines in the operation schedule. One is January 1st to start grazing, and then March 1st to plant in rows, which should be the plant the summer pasture. That's it, right? And then if we go back to, if we go to another edit Apex input menu, under Apex input files, edit Apex inputs, we have Apex control table available for editing. Apex control table is the one that we can set simulation period and first year of simulation, month and day of date of simulation to start. So this NBYR is the number of years to simulate. So in this case, we have 30 years. Actually, it was 40 something default, and then actually I was playing with it a little bit. So now it's 30. So you can click the edit control button on the right here to actually edit the numbers. So, and then this was like, I don't know, 1950 something with the default. Basically what it does is it just, reads all the DLY file and then put the all list date available in the daily, weather data, and then write it here to maximize, to simulate the maximum period available with the daily weather. But of course, we can choose to simulate only, let's say, 1980 or like, let's say, 15 years, right there. And then from January 1st. And then other options like, okay, do we want to print daily, monthly, or annual interval? What ET method do we want to go for? Penman Monteith, Hargreaves, Priestley Taylor. Those options are available by selecting here. Of course, we have the default options all kind of predefined. If you want to stick with those, then we can save it. Now we just set it to simulate 15 years starting from 1980. And then the summer pasture is written as 1 year rotation with just 2 lines, right? We'll rewrite in Apex input files and then rerun. Now you see 15 years only, right? It was 40 something years. And now you go back to the folder, exercise folder, txt in out folder, and you see the time it is written. So if you click to open the ACY, it starts from 1980 for 15 years, which is up to 94, because 1980 is the first year. 94 has to be the 15th year. So see, many HR and many sub areas have summer pasture, right? Actually, the majority. Only one sub area has corn. And this summer pasture, while having only 2 lines in the operation schedule, like a start grazing and then plant, it actually repeats that over years during the entire simulation period. If you had year 1 summer pasture and then year 2 soybean, then this particular sub-area in year 2 should have had soybean, right? Not summer pasture. So those are the kind of management schedule to create and then actually use to simulate apex. One thing I'd like to do is, according to the annual crop yield data, let's look at this particular sub-area. This particular sub-area, the output includes the name of the crop, and then this is grain yield, forage yield, total biomass, and then others. All the descriptions, you can find them from the user manual. Apex user manual has all the descriptions. You can just search for YLDG, then you will find what really that means, how this name YLDG is defined in terms of Apex output. So user manual has all those information available as your reference. But let's say, let's look at this first sub-area, because we have 14. I'd like to just look at this very first one for this particular practice. We had about 20 tons per hectare biomass produced in the first year. During the growing season, we had quite a bit of water stress days, more than 110 days of water stress days, meaning while the summer pasture was growing, more than 110 days, 111 days, the summer pasture had not sufficient soil moisture to grow for the day. So its exploration, transpiration requirement was not met during those days. But then this is the days that water stress was the most significant growth stress factor among water, nitrogen, phosphorus, temperature, potassium, ammonium, toxicity stress, and then salt stress. So comparing all these different kinds of stress factors, water stress was the largest during this many days. 20 other days, summer pasture had the greatest nitrogen stresses. So that day it may have had water stress, but not as significant as nitrogen stress. So these are the kind of indicators what were limiting resources for the summer pasture to grow in that year. So for this, noting these two limiting factors, couple practices I'd like to do today with the ARC Apex interface program is that I'd like to add irrigation to the summer pasture operation schedule, and then see if that applies irrigation water to this particular sub area, and then hopefully show some non-zero value on this column, because this is total annual irrigation volume in terms of millimeters. So hopefully I want to see, let's say 100 millimeters, 200 millimeters of irrigation water volume here applied. And then after that, well, it does have some grazing practice. So manure, fertilizer will become available as a nutrient, but it's not chemical. Fertilizer has not been applied. So but then automatic P fertilizer is enabled there, as you can see here. But I'd like to add automatic fertilizer operation to the operation schedule for inorganic nitrogen fertilizer application. Just for the sake of simulation, and then see if that helps reduce nitrogen stress. But the first thing is a water stress to handle. I'd like to see how this makes a difference. So we're gonna save this scenario as baseline. Save simulation. Let's see, because I'm not really convinced of what I'm doing. So baseline txt in out has ACY, so that means it reflects the recent changes, editings we did in the print file. So this is good. And then now what we'll do is continuing with arcapex mask. We're gonna go to the Apex input files. No, I'm sorry, database, yeah, and then databases to edit summer pasture. Okay, and then in doing so, what we need is okay, so how do we apply automatic irrigation? And if you received an email from me this morning with 2 files attached, both PDF. One of them is titled Conservation Practice Manual, parenthesis training.pdf. And this slide kind of summarizes the irrigation, practice fully described on page 4, 5, and then beyond. So the manual is wordy, right? But it's very detailed. Here with this slide, we will be just adding, changing these inputs used in the Arc Apex inputs, and then a rerun Apex, okay, to apply automatic irrigation. But if you open the conservation practice manual, then it has all the same settings kind of elaborated, described. So we'll go with this. So I don't know, there's seems no way to share a file through this session. So I'll share this with you later. This printed slide, in case this helps. But I'll just follow these settings here. Okay. So now we're gonna first open the operation schedule for summer pasture, and then make sure that IAUI is set to 500. So operation schedule, and then we'll pick summer pasture, and then see. We edit. Okay, so we made it editable now, and then you see IAUI, that's irrigation setting. That's tillage ID if automatic irrigation is turned on, and then as you can see, it is set to 500. So you're good. So I'm not gonna really change it, and then I'll exit it, because operation schedule is that's it. We're not adding anything to operation schedule. We are setting the sub area to do automatic irrigation. So after that, we're gonna do the settings in the sub area file, okay? Which is a few things like NIRR, IRR, VIR, and those things in the sub area file. So I'm gonna just kind of move it down here to deal with Apex inputs. So we're gonna go to the edit Apex inputs, and then we're gonna go to the sub area file. Okay, and then we have 14 sub areas, and which sub area was it that subarea ID 13. So make sure that you have each subarea has subarea name, number, and then ID. Subarea number is just incremental numeric ID number, but then subarea ID is more like a subarea name. They can be the same or different. And as you can see here, ArcApex created subarea file, name these subareas differently, giving different IDs. So here we're talking about subarea number 1, ID 13. And back to here. So subarea ID 13 was the one that we wanted to add the automatic irrigation. So if we go to the irrigation part, so this if you check, you can check the management for this particular subarea set to 7, which is summer pasture. So seems to be the right one. Then we will go to the irrigation tab, and then there are things that I wanted to modify. So let's see this NIR, that's a rigidity. So this is binary 0 or 1. So 0 being okay, application rate will change every day depending on the demands. So let's say we will set by soil moisture content deficit. So meaning, okay, what is the current soil moisture content compared to the field capacity level? If the current soil moisture content is 75% level of the field capacity, then we'll irrigate only the amount that's equivalent to 25% of the field capacity level. If soil moisture content is only half of the field capacity level, then the 50% will be the daily irrigation volume to meet the field capacity level water content for the day in the soil. So that will kind of dictate that flexibility. If it's 1, then it is just a fixed amount irrigation. So we want to set the fixed amount. Okay, so number 1. And then what about IR? We want to do sprinkler irrigation. So 0 is rain-fed, dry land, no irrigation. 1 to 5 or more. Let's see, we have some drip irrigation and so forth. Yeah, 5 is drip irrigation. So sprinkler, furrow, fertigation, lagoon, and then drip irrigation. So drip irrigation actually will apply water directly into the soil. So there's no runoff to create from a drip irrigation system. But the sprinkler irrigation can have a portion of the daily irrigation volume lost in surface runoff. So we're gonna select the sprinkler irrigation. And what else? We want to go with crop stress. So BIR is a parameter that kind of offers hybrid options. If it's a 0, then it's a manual irrigation. If it's a 0, then okay, when you have irrigation operation set in your operation schedule, it will irrigate the field or subarea. If you don't have anything set in the operation schedule in terms of irrigation, then setting the BIL 0 will make this particular subarea completely rain-fed and no irrigation. If it's a value between 0 and 1, then that means you will irrigate based on plant stress level. So it's actually 1 minus plant stress. That's BIR. If you put anything between 0 and 1. So if you put 0.9, that means if water stress hits anything more than 10% of the plant transpiration demand, then it will trigger irrigation for the day. So I'm going to put 90%, you know, of the time the water contents in the soil will meet the demand as to trigger water irrigation. And okay, efficiency, that's EFI is right there. So if you click that, it's a kind of fraction of irrigation water that will be lost in runoff volume. So I'm not really simulating that for now. So I'm just keep it at 0. And then the next is VIMX, that's an annual maximum volume of irrigation. So cumulatively, you know, you want to limit the irrigation volume not to exceed certain you know cubic meters. So I'm sorry, millimeters units. So we'll set like okay, 1,000 millimeters. About that? That's quite a lot of amount to irrigate. But just you know, we'll set it that way, and then minimum, and then ARMN, ARMX. Those are you know each day minimum and maximum irrigation volume. And that can be whatever 10 and 30 millimeters to soak soil. So we'll set it that way, and that's it. That's it. The next page is actually fertilizer. So we are good with this, and then so we'll save it. Boom, and then exit, and then right, select, okay, and exit, and then what? Rerun. Okay, so run is complete. And then what we need to check is if the irrigation is applied first. And then second, oh, it is not. What's going on? Oh, it's baseline. Okay. That's baseline. We have to go back to the default. So now you see the irrigation 660 millimeters has been applied to this sub-area. All others still remain at 0. And what did it actually, how did it influence? See the water stress days. It was 111, something like that, down to 3, right? And then look at the biomass amount. We can actually open the baseline scenario side by side and then compare values. It was 1998 tons per hectare of total biomass. Now with that, you know, about more than 100 days of you know water stress removed, it grew much bigger, from 20 to 31 tons per hectare. So removing the water stress days substantially actually influence dramatical increase in the biomass, you know, production, and that will have had other impacts like let's say inorganic phosphorus amount reduced from 203 kilograms per hectare at the end of the year down to about 200, so about 30 kilograms per hectare more of phosphorus being used to grow the pasture, and you know other things. And if you notice carefully here, look at the nitrogen stress. It was 20 days, but then it increased to 104 days. Well, did it use more nitrogen? Yes, it used more nitrogen to grow more biomass, right? To build more biomass. And also 660 millimeters of irrigation, this one, may have resulted in, you know, plant available nitrogen leaching to down, you know, subsoil layers. And maybe recharge groundwater and then actually lost from the root soil root zone. So as a result, the summer pasture may have had greater nitrogen stress days. And one more possibility is that, because we have less water stress days, maybe the second largest, stress factor being nitrogen now in the baseline is now the most, critical nitrogen, stress factor. So it is counted as a nitrogen stress day. So all these will combine to make much greater nitrogen stress days for this particular sub-area. Now, what we want to do, we want to go ahead and then add automatic nitrogen fertilizer to the same sub-area and then see if we can reduce nitrogen stress days in this sub-area. So that will be in the conservation practice manual. That will be page 9. Page 9, yeah, page 9. So, okay, back here. And if we go to the next, boom, we'll just do nitrogen fertilizer because phosphorus is already there. So those settings involved with automatic nitrogen fertilizer are these 3 items. So basically type of fertilizer or fertilizer ID to set in the sub-area file, and then stress level like a BIR. PFT is the same as BIR. At what stress level, we want to trigger fertilizer application, and then rate when triggered. How many kilograms per hectare of fertilizer do we want to apply? So those 3 are the things that we'll be setting in the sub-area file. So we'll go to the sub-area file. Edit, Apex input, and then we'll go to the sub-area file. Then here, what was the ID? I already forgot. That was 13, right? Second to the last. So 13 has irrigation details already set, and then what were the things that we wanted to do? ID F4, so that will be fertilization, and then these are all different kind of arrangement for automatic application of fertilizer from lagoon, from manure. This is phosphorus, and then others. So we want to put 53 here, nitrogen, and then there were a couple other settings here, right? So BFT, that's the stress factor to trigger fertilizer application. If you click it, it says in the parameter detail window, BFT is a nitrogen stress factor to trigger automatic fertilization. And then actually there are some other options than between 0 and 1. And then last one was FNP4, this one. That's auto fertilizer application rate. So we're gonna set how much? 20, okay, 20, and then we'll see if this is sufficient. It can be 20, it can be 60, or we can experiment like 600 kilograms to see, if that provides excess nitrogen, and then where will that nitrogen, additional excess nitrogen, will go will it stay, or will it just make runoff a loss, or leach to shallow aquifer? So we're gonna save it. Exit. Rewrite Apex files. Select all, and then OK. And then rerun. Boom. Now, one of these files should have been updated. Maybe this one. So it was 104, and now it is 11, right? So nitrogen stress days reduced from 100 to 11 days, and then water stress days increased slightly. That's again because we take the largest stress factor for the day among these, how many? 7 different stress factors that limit daily growth of biomass. So because we have a reduced number of nitrogen stresses every day, the nitrogen stress level could be like a 15%, 20%, and then comparing with water stress, this can be smaller than that. Then water stress they will increase. So that's what's going on. And now look at the biomass amount actually increased in the baseline. We had it 20 tons per hectare with more than 100 days of water stress and then 20 days of nitrogen stress. Now, when we applied, irrigation water and then additional chemical fertilizer, elemental nitrogen fertilizer to the summer pasture, the biomass production increased from 20 to 51, more than 2.5 times greater amount of biomass was actually made with these additional, management practices. So environmental benefits and trade-offs will also follow suit with implementing these practices. Because with additional water, soil will continue to stay wet, and any additional rainfall will make the soil saturated, and then therefore, some inorganic nitrogen, especially nitrate, will actually be denitrified and then get lost in nitrogen gases form, like nitroxide. Phosphorus will, let's see, additional fertilizer of nitrogen fertilizer application will make the inorganic nitrogen amounts greater in the soil, and therefore a lot more nitrogen will be mobile and then actually transport laterally and vertically, and therefore will get lost proportionally. So those will be, 400. That's a lot of phosphorus. I mean, nitrogen fertilizer. So, wow. Because this is automatic, fertilizer application. This is a good way to kind of, get an estimate of, how much actually nitrogen we will need to keep the nitrogen stress level below this, much. And then, here we have 400 kilograms per hectare of nitrogen we need in fertilizer application. That's the stuff that we learned. And then 810 is like, this is amount of water irrigation volume that we need to apply to keep the water stress level below 10% for this summer pasture system. So these are kind of the reference numbers that we can learn from just running the model with automatic application settings. We can also add these irrigation and fertilizer applications to operation schedules to make more like a event operations. Like okay, this day we'll irrigate 20 millimeters. That day we'll irrigate 30 millimeters. This date we'll apply this particular fertilizer by 60 kilograms per hectare, something like that. As part of the operation schedule, we can make it that way. Or in terms of irrigation, we can actually start automatic irrigation and then stop irrigation by adding those lines into the operation schedule. So we can go on and on and on to go through all those things, but it's about an hour before 4 p.m. So I'm gonna stop demonstrating RKPEX, interface program, and then doing hands-on exercise here. But I think I showed you what it takes to modify, construct a model using the Arc Apex program, and then modify databases and input files, and then rerun Apex with certain, configuration changed and updated, and then read outputs from the new settings, and then kind of interpret how the results can be different from the earlier runs before we modify the setting. This conservation practice manual. This Evelyn is an RCS, person here at Temple working with us in the SIP project. She's a coordinator, basically leading the SIP, modeling work, and then she kind of, summarized what it takes to set up a particular operation, management practice, and they are like irrigation, fertilizer application, different types of fertilizers, tile drainage, and many others, filter strips and terracing, contour farming. Many other things are available here with very specific details and guidelines. So you can just, review those sections that you're interested, and then modify Apex settings to implement these practices with the Apex model, and then see how results change, outputs change in terms of crop growth, in terms of nutrient dynamics, and in terms of water balances, and then you can do interpretation of it, why this particular terracing practice will reduce surface runoff and then increase water recharge, things like that, and so reduce nitrogen availability, things like that. All those are simulated in a linked way, and so interpretation has to be done carefully and comprehensively. So I'm gonna wrap up here the demonstration for today. Tomorrow we will continue, but not with the Arc Apex. We're gonna stop Arc Apex here, but then we're gonna introduce you a very convenient tool called Apex Editor. That Apex Editor is really powerful and convenient when you have your Apex files created out of Arc Apex or WinApex or Apex Editor itself. Once you have your Apex input files created, then there are so many things that you can do a lot more conveniently than by using Arc Apex if you use Apex Editor. So we will use Apex Editor as the main tool to set up many different things, including management practices, conservation practices, and other things tomorrow morning sessions, during the tomorrow morning sessions, and then a little bit after lunch, and then we'll do sensitivity analysis and calibration practices in the afternoon tomorrow. then the day 3, we will address all the Apex model flow integration stuff during that day.